let's keep going talking about reflections. So I want to graph the function negative root x and then find the domain and range. Okay. So this is basically the square root function, root x, which we know how to graph, but anything I got out is now being multiplied by -1. So if I used to get out the point x comma y, after multiplying the y value by -1, I now get out x comma -y. So I used to get out these values here. The root of 0 is 0, square root 1 is 1, and so forth. But now I get out exactly the negatives. So if I used to get out these positive values of y, I'm now going to get out these negative values of y. So all I have to do is take all my positives and make them negative. If I had negative outputs, I would multiply them by 1 and they would become positive. This particular example does not have any negative outputs, but if they were there, they would become positive. So the domain is still 0 to infinity. Nothing changed that way, but the range definitely changed. Okay, I used to only get out positives and 0, and now I get out negatives up to and including 0, because everything I got out got flipped. So this sort of reflection does not change the domain, but it does flip the range. Okay. I like to think of this as being the same thing as a vertical stretch, just by a negative amount. Because remember, a vertical stretch was when you had a times f of x. And if a is negative, you still do the stretching, it's just you also have to incorporate this reflection across the x-axis. Okay, but now let's look at the different example, negative x cubed. Notice this is not like a vertical change. This is like a horizontal stretch where you had f of ax, but now a is negative. So if a vertical stretch with a negative number meant reflect across the x-axis, take your positive y's and make them negative and vice versa. This sort of reflection is any x's that used to be negative should now be considered positive and vice versa. So this is a reflection across the y-axis. So any point that we used to get out, xy, will now get out with the same value of x but negative. So that is accomplished by reflecting across the y-axis. Okay, so what we used to get out here for these positive values of x, we get out the same values for these negative values of x. What we used to get out for these negative values of x, we now get out for these positive values of x. And that's accomplished by this sort of reflection. This is probably not the best example. I'm not sure why the book chose it, because it also looks like a vertical reflection, because it happens to be the case that negative x cubed is the same thing as negative x cubed. So you could have thought of this as a vertical reflection, but if it's written this way, you should be thinking of it as a horizontal reflection, this sort of thing. Okay. So what about, for example, if I know how to graph y equals x plus 2, okay, it looks like this. What about y is equal to negative x plus 2? Well, then I would do a reflection across the y-axis, and it would look like this. It's not a vertical reflection. Okay? If I did a vertical reflection, it would look like that. No, this is a horizontal reflection, and I get that solid line right here. Okay, let me clear off all of the pen marks. So the domain in this particular example is still all real numbers, because this does actually change the domain. It exactly reverses it, but the domain of our original cubing function was all numbers, positive and negative, and if I flip positives and negatives, I still end up with all numbers. The range is actually not changed by this sort of reflection, because what I used to get out over here, I now get out over here, and what I used to get out here, I now get out here, so I'm getting out the same values. So the range of the cube function was all real numbers, and it still is. Okay, so if you have this f of ax, where a is negative, that is a reflection about the y-axis. So let's take a function we know how to graph, x squared. And what we're going to do is we're going to try to figure out what the graph and the function is for the same thing, but with these three steps in this order. Well, let's talk about the graph first. So the first thing I'll do is I'll take the graph and I'll shift it to the right by 3 units. So it's basically the same curve, but instead of this intercept being at the origin, if I shift it to the right 3 units, it needs to be here. Then I need to reflect it across the x-axis. So instead of opening up like that, it's going to open down like this. But I still have the same intercept. Okay? If I reflect a y value of 0 across the x-axis, it's in the same place. Then I need to shift everything down by 2 units. So it's going to look like this. I took that same intercept and I shifted it down. But what function will accomplish this? So try to start with x squared and apply these 3 things. First, what would you do to shift right? Then what would you do to reflect about the x-axis? And then what would you do to shift down by 2 units? Okay, I'll pause here. Okay, so to shift right, you would just replace x with x minus 3 inside that squaring. To reflect, you'd multiply by -1 outside the squaring because we're reflecting across the y-axis, the x-axis. And then to shift down by 2 units, you would just take a -2 at the end there. So this function here has this graph. How about the function x squared over 2 plus 1? Graph it, find the domain and range. Okay, so again, I'll pause for a moment, try to complete this example, and then we'll go through the solution. All right, so the x squared over 2 might not look like any of the things we did, okay? Because everything was, well, you're multiplying by a, and now it looks like we're dividing. In that case, you should imagine it as multiplying by 1/2. Remember, that is the same thing. So take the following steps. The first thing we're going to do is start with the squaring function. Next, we're multiplying by 1/2. So the original function, I'll draw on here, looked like this. Okay, for example, it contained the point 2, 4 and -2, 4. But now everything is squished by a factor of 1/2. So the points that were up at height 4 are now at height 2. The points that were at height 1 are now at height 1/2, and so forth. Okay. The next thing we have to do is take this squished curve that we just made and shift it up by 1. Okay, so there's the graph of x squared over 2 plus 1. Now, what's the domain and range? From the graph, try to figure it out. Okay, I'll pause for a second. So the domain is still all real numbers, but the range is only from 1 to infinity. Everything got shifted up by 1. And I'm going to go back to when this problem was first given. So even without the picture, we could still figure this out. Okay. So here is our function. And we know that x squared has domain everything, and the range is just from 0 to infinity. Okay. So the first thing we do is multiply by 1/2. That absolutely does not change the domain, okay, because the x part didn't change. It was just once the operation was completed, I multiplied by 1/2. So whatever I could have plugged in, I still can. So the domain is the same. Now the range, the numbers I get out are now going to be half as big. But I used to get out everything from 0 to infinity, and now if I make them all half as big, it's still 0 to infinity. And then finally, I'm going to add 1 to it. So everything I could have plugged in, I still can. Adding 1 doesn't really change that. So the domain is still from -infinity to infinity. Now the range does change. Okay, I used to get out from 0 to infinity, and if I add 1 to everything, I move all of that up. So on the number line, if I used to get out 0 to infinity, but then I move everything to the right by 1 unit, now I'm only getting out everything from 1 to infinity. Next example. Graph negative root 2 plus x plus 1. Find the domain and range. We've got all sorts of transformations to worry about, and we've got to be careful about what order they happen in. Okay. So the first thing we want to take care of, you should usually try to find your x's, work out from there. Okay. So the first thing is this 2 being added to x. inside the square root, this is going to look like one of these things. But we don't really have an x minus something. It's 2 plus x. So to match what we're used to dealing with, we should replace that 2 plus x with x minus negative 2. And here we can identify that. Okay, if I have that, let me do it on it. This now tells me this is going to be a shift, this x minus negative 2. Is it right or is it left by 2 units? It's going to be left. Okay, so at a certain point, we're going to have a left shift of 2 units. So the first thing that the book does is to multiply by negative 1. So we get this negative root function. Now we're going to do this left shift. Okay, so instead of root x, which then got reflected down here, now it's been shifted left by 2, and finally up by 1. So here's the graph of negative root x plus 2 plus 1. Okay, so using the library of functions and these techniques, we can now graph without using a calculator, just using these techniques, pretty accurately get graphs of lots and lots of different types of functions. So take a look at problems from this section, get some practice with this. It's really convenient to get a handle on this type of thing involving horizontal shifts and vertical shifts and horizontal and vertical compressions and reflections. You can start to really recognize what graphs represent which functions and understand them a lot better. If you rely too heavily on, I can always just punch this into the calculator and it gives me a picture without ever understanding how the picture was created, you can't easily recognize when you accidentally enter it wrong, and it gives you something that doesn't make any sense. Okay, so a lot of times, you know, back in the good old days when we had in-person exams, a lot of students would like raise their hand and say, I have a question, my calculator gave me an error. And fundamentally, it's because the student entered something in wrong, but doesn't know the material well enough to recognize that they asked the calculator to do something ridiculous. They think their calculator's broken. I unfortunately recognize that they just don't know what's happening. Okay, if you rely too much on the calculator, then if you accidentally put something into the calculator wrong, you're never going to recognize that mistake.